Hello, and welcome to Telecom Infrastructure to Support AI, powered by Award Solutions. My name is Reece, and I'll be hosting this webinar today. A little bit about Award Solutions. We're a proven leader in the technology training field, having been in the field for over 22 years. Our areas of expertise include artificial intelligence, machine learning, automation, data visualization, Python, Ansible, as well as data insights. We also cover things like 5G, IoT, CBRS, and 4G LTE and VoLTE. As a special thank you for being a part of our webinar today, I'd like to extend a gift to you, and that is to save 40% on any e-learning title or any tech primer through the end of November using the coupon code you see on your screen. Likewise, if you would like to connect to me on LinkedIn and send me a request, I'll also send you the coupon code via LinkedIn. Before we get started, my name is Reece, technologist with Award Solutions. I've been in the technology industry, the telecommunications industry, for over 28 years, 19 years with Award Solutions, and my focus is on artificial intelligence, network transformation, 5G wireless technologies, as well as consulting and custom training. Our agenda for today is as follows. We're going to first talk a little bit about what is an AI model and what does it mean to do AI model deployment. As part of that, we're going to look at two key use cases. A local deployment, where we're trying to deploy this model locally where the AI application is running, and a remote deployment, where we're going to use some type of a application programming interface to communicate with that remote entity. At any time, if you have questions during our presentation, please feel free to go onto the chat and send a chat and let me know the question. I'll answer it as I can. So let's start with a discussion on model deployment. Our basic AI and automation lifecycle is composed of four basic parts. We start with a large amount of data. This large amount of data can come from any system. It can come from a telecommunication system, it can come from an enterprise system, but it needs to be data that will help us solve the problem that we're trying to solve. From that data, we're going to actually do model creation. This is the part of the system that we typically refer to as training. This is where we're going to train a model to be able to make a prediction based off of the data that we gathered over here. Now, once we've trained a model, we want to be able to use it someplace. And that's where we do model deployment. This is where we save that trained model so that we can have new data come in. We'll be able to make a new prediction based off of that data. Now, after we've saved that model, we need to be able to deploy it someplace so that we can utilize it for a new incoming request. Now, what is our ultimate goal? Our ultimate goal is to be able to do some type of automated action. Now, early on, it may need some type of human intervention. So for example, I may design a system where someone makes a request via a chatbot, and that request is sent to a specific human who can solve the problem. But over time, we want that to become more automated in nature. If we go through and do any retraining of the model, we then need to redeploy that new model. So the emphasis that we want to focus on today is really, what does it mean to deploy a model? What does it mean to save that so that we can use it later? And the reason this is such an important discussion is because this is going to happen many times, whereas this training will happen a very few times. Let me give you an example. If I'm trying to do a self-driving car, I need to train the model, many models that are in the car, so it can drive around the city. It can make all of the appropriate decisions. Now, while I'm driving, every few seconds or every second, I'm going to make many decisions. Is there a pedestrian in the crosswalk? Is the light turned red? Do I need to make a left-hand turn here? So that will be using a deployed model that was trained using a lot of data to build this model. So we need to be able to deploy this in such a way that we can utilize this in an efficient manner. So what is a model? So with any of our machine learning applications, what we've done is we've built some type of an artificial neural network. And that artificial neural network will have an input layer, it'll have an output layer, and it'll have a number of layers in the middle called hidden layers. And it'll have a number of neurons on a per layer basis. So what are we training? Well, what we're training when we go through this model is we're training how to make a prediction. And really what we're training are weights that are on each of these lines. So in this simplistic little chart, what I'm saying is with my 3 inputs that I have coming in, I'm going to try to learn how to make one of 3 predictions. And I need to train all of these weights. What I want you to envision is if I am trying to come up with some type of very complicated function. I've got an f of x equals y. The hard part is, given a very complicated x, what should this function be so that I can get an expected output? So this slide is really focusing on training. How do I train that? But at the end of the day, when I'm trained, what I have is I have a set of weights associated with each of these lines in this graph. So now if I were to take a new picture and want to run it through this model to say, is this a cat, a dog, or a squirrel? It would use the pre-trained weights and it would give me a prediction that says, oh, it's a 90% chance this is a cat. And so it would say cat. So we have all this data. We're going through training. We're feeding the data forward. We're then doing something called back propagation to update those weights. And we're going to keep doing this loop until we get an appropriate amount of error. So what I like about this slide, what this slide is helping us see is this is really those weights that we were talking about. So once I have those set, I should be able to store them and then use them again. So this is an example of this particular neuron. And that neuron has data coming from the previous neurons, and it's applying these weights. Weight 1A, weight 2A, weight 3A. It's doing a sum, and it's sending something out to Q, and then we have a weight applied to that. So this can get quite complicated. For each of these layers, we're going to have a number of weights associated with this, and these weights we'll have learned based off of the training properties, as well as we've decided a number of other factors. So for example, we have something called a transfer function. So that transfer function needs to be stored. We have a certain number of neurons, and so those number of neurons need to be stored, and so on. So before I go to the next slide, what I wanted to do is I wanted to show you a demo of this. And so I'm going to jump over into my lab. And what I have in my lab is a very simplistic AI algorithm that I've built and I've trained. And so what you see on your screen is the code for that algorithm. And really there's only 2 lines of code that are interesting. I'm loading a model, I'm inputting some data, and then I'm doing a prediction down here based off of that model. And that's all I'm really doing. So let me run this. Let me show you this in action. So this particular model is designed to do churn prediction. So what I've done is I have a set of data that I picked up from the internet, and I've trained this model to look at profiles and say, is this subscriber likely to churn? So now what I want to do is I want to use that data for a new prediction. So we're going to do this twice. The first time what we're going to do is I'm just going to use default values to make life easy on ourselves. So I'll go kind of slowly so you can kind of see it, but really it's not that important. All this is saying is I've got some default value for each of these parameters associated with a given subscriber. Once I'm done, it gives a prediction. Based off of all these default values, this customer is likely to churn. Take some action. Now, that's all my algorithm does, is to give me that information. In the future, I'd like to have it do something, like maybe initiate an email to someone that's on our customer retention team. Now let's do this again, but this time what we're going to do is we're going to enter different values just to see what happens. So we'll say this is a male, senior citizen, does have a partner, does have dependents. It's been with the company 30 months. Does have cell phone service, does have multiple lines, doesn't have internet, doesn't have streaming TV, doesn't have streaming movie service, has a 2-year contract, paperless billing, uses a credit card, $35 a month, which is a very low bill, and has spent $600 total, not likely to churn. So I don't need to take actions. So now we've seen a very simplistic example of an AI model in use. Now let's say what I wanted to do is I wanted to give you this trained model. Well, this trained model is in a file format called an H5 format. So what I've done is I've installed a piece of software called an HDF viewer. And what that does is it allows me to read this model in and then look at those weights. So let me give you just a little bit of background on the nature of this model that I have. My model has 22 input layers. And those 22 input layers are those different features that we looked at. Male, female, senior citizen or not, how much money are you paying in your bill every month? What's the total amount you've paid? For the sake of this model, I've created 2 hidden layers. One I chose to have 23 nodes, one I chose to have 7 nodes. And then lastly, I have one output layer. And that one output layer, that one output node is really yes or no, because that's all I'm trying to determine. So this is a very simplistic model. So that being said, I can now look at each of these models and say, so these are all of those weights that we were talking about a few minutes ago. So the weight from input neuron 0 to hidden layer 1 neuron 0 is this. From 1 to hidden layer 0 and so on. And you can see all those values are quite different. And if we did an analysis of this, we would start to see a little bit of interesting information about what features are more valuable than other features. This is the number of, or this is all of the weights of the features, or of the, between hidden layer 1 and hidden layer 2. And then this last one is all of the weights between hidden layer 2 and the output layer. And there's only one output layer. So this is those weights. So you can see this file isn't very big. I could come here and look at the size of it. This file is only 36, 37 kilobytes. It's fairly small. So this is something I could send to somebody else so that they could do this exact same exercise. So the first thing I want us to talk about is, this is what it means to deploy a model. So that being said, so what? So what do we do with this? So there's two options once we've trained the model. Once we have that .h5 file that we looked at a second ago, we have an option of deploying something locally or deploying something via an API call. Another way I could say is, this is my remote option. And we'll take a look at each of these in turn. So let's look at the remote, or the local deployment first, the local deployment. With the local deployment, what's happening is we're going to build an application where the AI algorithm is co-located with whatever device is producing the data. And that's really the important piece of this. With local instantiation of this model, my AI model is co-located with the data source. So in my simple example here, I've got a video camera. And this video camera, we could say it's a security camera, or it's some other type of sophisticated camera. This AI algorithm is actually going to be co-located inside of that video camera. So for example, if we were doing some type of alerting of some type of problem, the camera would have to be the one that initiated the alert. If we were doing some type of AI algorithm to do image recognition, or to do some type of analysis of the scene to provide some type of a mood, or to do some type of focusing or filtering of the data, it would have to be co-located with that camera. Well, it makes sense if it's talking about something like a camera, especially if it's a very expensive camera. But what if we're dealing with like a webcam, a security camera? Do I really want to have this extra chip that's doing, in this case, an autofocus? Do I want this extra chip that's doing AI in every camera? Well, not if I can avoid it, because that's going to be an extra cost. Think about IoT type devices. If I built an AI application that's co-located with every IoT device, that might be very expensive, even though it may only add a few dollars. It may add $5 or $10, but if I'm deploying millions of these things, $5 or $10 is a lot. So we've already looked at this FDF viewer to see what that application is. But what's happening, just as I showed you in that demo, what's happening is we're loading that model in, we're taking new data, and we're running that model. And we're doing that over and over and over again. So there's CPU power that's being used to run that model. Now, there's a lot of chips that are being developed so that they can be able to run this model much more efficiently. So for example, a number of manufacturers are building chips that are designed specifically for what's referred to as AI inference. And AI inference is nothing more than what we looked at. It's taking a trained model and running new data through it. Now, if you're dealing with something like my simple little churn data, it doesn't take much processing power. that if I'm dealing with something like self-driving cars, this becomes very, very big. Very, very big. So that's local deployment. Now, we could build that into the application itself, and there are a number of instances where we may want to build this into the application. For example, if I'm doing some type of orchestrator, well, maybe I'm going to build the AI algorithm into my orchestration engine. Maybe if I'm doing some type of a chatbot, I'm going to build the AI inference engine into my chatbot. Maybe if I'm doing, we've already looked at self-driving cars, we've already looked at image recognition, but what if I'm doing some type of a network management system? These are examples where I might deploy that locally. When I want to deploy it locally is when time is of the essence. It needs to be real time. I don't want a self-driving car making a query across a network before it makes the decision if it should apply the brakes or not. That's not going to work in the long run. All right, cool. Let me pause for a second, see if anybody has anything in the chat. Questions, comments, thoughts at this point. Excellent. So we've talked about two of our three main ways that we want to do deployment, or two of the three main topics. We've talked about what model deployment is overall. We've talked about local deployment, and now I want to move into remote deployment. Is this a telecom application? So absolutely. The telecom application we're thinking about from a local perspective is where I'm wanting to do something that's potentially built into a cell phone or built into the network itself, be it an orchestrator, be it some type of network management system. Where the telecom piece is going to come is really the remote deployment. And in the remote deployment, we're going to see that there are a lot of additional ways that we could deploy this. So it's a great question. Thank you for asking that. So let's look at remote deployment. So typically when we do a remote deployment, we're going to do some type of an API call to some place that's going to do that inference. So let's kind of break that down a little bit. Let's say in this simple example, what I have is I have some type of system represented by this robot. And so this robot is going to receive some information in some way, whatever that information is. Now, this robot is not built with the information or the AI inference engine inside of it. So what it's going to do is it's going to do an API query to a server that's running in the web someplace that will receive that query and then provide a response back. And then it will take action based off of that response. Now, that may result in another query depending on the nature of the problem we're trying to solve. But that's really the key of a remote deployment. So now we have two questions that we need to ask. The first question we need to ask is time related. How much time are we allowed to take in doing this response? And then two, who are we going to query to do this response? Let me give you a simple example first, and then we're going to get into more of a telecom example next. So let's just say for the sake of argument, what I wanted to do is I wanted to build a chatbot. So how much time is allowable for the sake of a response to a chatbot? Well, the response can be on the order of seconds. Well, not 10 seconds or 20 seconds or 30 seconds, but at least we'll say 1 to 3 seconds. Now that may seem like not a lot of time, but in computer time, that's an eternity, right? That's 3,000 milliseconds. And we can do a lot of things in 3,000 milliseconds within a computer. The second question is, who do we want to actually do that AI inference? And so I've got an example where what I was using is I was using something called Dialogflow. And what Dialogflow would do is we would receive a request, we would receive this info, in this case would be a chat. We would send the chat to Dialogflow. Dialogflow would respond, and then we would provide some type of action based off of what that chat really meant. Now, the reason I use Dialogflow is because they had the trained model. I didn't have to do anything. All I had to do was use what they'd already provided, use the API engine that they have already created. Now, let's change this example a little bit. Let's say instead of doing something like a simple chatbot, I want to do an example that is some type of augmented reality. So in augmented reality, I have some type of augmented reality glasses, and I'm looking out at a city street. And what the augmented reality glasses are doing are placing pictures or labels on the business that's in that building. So I see over to the right is a Starbucks, I see a McDonald's, and I see a Burger King. As I move my head around, that label needs to move. That's what's critical. As a matter of fact, the time span on my AI application is now on the order of around 20 milliseconds. So if I were to go to a web-based application, that might be that might take too long. So now I have a question of, I'm not sure who could provide this service. And that's going to give us an opportunity that we're going to look at here on the next slide. So a direction that a number of telecom operators around the world are getting into is something called the intelligent edge. Another term that you may hear for this, and this is really the heart from the telecom perspective of what I wanted to talk about today. Another term that we hear a lot of times is something called MEC, which stands for multi-access edge computing. And really, in either the case of using the term edge or using the term MEC, what we're trying to do is we're trying to deploy servers closer to the users. So here's all of my wireless subscribers out here, so that they can provide services. So my service or my applications are provided on this set of servers. So now we have 3 different places that we could deploy this AI inference engine. I could, 1, deploy it on the public cloud. So this would be the same as if I were using Google or Amazon or Dialogflow, or there's another company that does some stuff with respect to analyzing or converting things to somebody else's voice called Lyrebird or whatever. So I could do an API call through this network out to the public internet. That's one option. And for a lot of applications, that's going to be fine. The second option is going to be, I could put this in a private operator cloud. And so then I could connect through the network and go to this operator cloud here. The third option for my stuff that's really sensitive is I could put it out here on one of these servers that are very close. Then something like my virtual reality glasses that I have here on this icon, I could access this and I could have a very low delay. How low? So what we're seeing is if this mech is set up right, I could have delays, 10 to 20 milliseconds. Whereas the public cloud is more on the lines of hundreds, thousands of milliseconds. And the private cloud will be more on the lines of around 100 milliseconds. So you can see it's quite a bit of difference in delay depending on what it is that I'm trying to do. So let's kind of turn this around. So if this is the application that I'm going for, now I have a new problem. And my new problem is really going to be where? Where do I actually deploy an application? And we've already talked about this term a little bit. I think this term is very important. It's called workload placement. So now when we bring up a new service, we need to make the decision. Which network are we going to deploy this onto? Or am I going to let this go out to the public cloud? Am I going to pull it onto a private cloud? Or am I going to use one of these mech servers here that are more geographically close to the subscriber? Going to really depend on the needs of that application. So that being said, how do I react to this as an operator? Well, now what I have to do is I have to build out my infrastructure. And this is really the key point of this whole discussion, is I have to build out my infrastructure so that I can have these different cloud environments available to me so that I can deploy my workloads appropriately. A number of operators are looking at deploying multi-access edge computing for things like AI inference. This could be the application that is used. So that being said, let me pause for a second. Questions, comments, or thoughts at this point? So from a training perspective, and this is also applicable to in some way to inference, we need to make decisions on what the hardware needs to be. Now, typically when we build a server, it's going to support CPUs. And they're very generally available. They're typically slower than GPUs, graphical processing units, but they are a much lower cost. There are a number of very complex inferences that may require something like a GPU. Special purpose, they're really only used for high computation, so things like AI and graphics processing. They're very, very fast. They're also very, very expensive. So now if I go back and I look at my intelligent edge picture, and I start to look at, I want to deploy this edge network what are some things that we can talk about with respect to the edge network? Well, one thing we can talk about with respect to the edge network is the fact that there will be many servers. And really what I'm getting at here is the fact that as I try to geographically distribute this around the network, I'm going to have a lot of small data centers where I'm going to need to deploy these servers. As a matter of fact, you may just have 1 or 2 servers. You may not have that many. So I'll need many, many, many servers in these locations. And then 2, the second question I want to ask is, what is the capability of these servers? So for example, I had the privilege of going to the GPU technology conference. That's NVIDIA's big AI conference back in March of this year. And on the exhibit floor, there was a individual from HPE, Hewlett-Packard Enterprise. And so he showed me their Edgeline product. And so they have a very small form factor Edgeline product. And it supported 8 servers. It was a tiny little box. It really wasn't very big. And the purpose of that was to go, for example, into a cell site so that I could deploy that and support these types of use cases that we're talking about here. And that was a very powerful server. And this particular server also supported GPUs. So if you had a very large amount of AI that you were trying to do in an area, this might be what you want to deploy so that you're able to speed up that processing and get those responses back even faster. So there's your fundamental question. As you're looking at a telecom network trying to support AI, where are you going to deploy those trained models? The training itself is probably going to be GPU based in some type of a centralized location. You're going to have a lab, and the lab is going to have GPUs, and that's how you're going to train your model. But really the question that I have is, when I go not to train, but to use the model, do I want to use CPUs or do I want to use GPUs? And if I'm using GPUs, do I want to have so many that I'm remotely putting them all around my network? Well, guys, I want to thank you so much for investing a little bit of time with me today and learning a little bit more about AI and telecom in general. And again, want to remind you, as a thank you, we're doing a discount on all of our e-learning and all of our tech primers. Webinar, the coupon code is webinar, and you can see the link there at the bottom of the screen. I want to thank you again. Next month, we'll be doing another webinar on the second Tuesday of the month, and that's going to be an introduction to data cleaning. Thank you guys so much. Reach out to me in LinkedIn if you have questions, and I'll see you next time.